Hi everyone, I am SS Kiran. I would like to discuss about semiconductor physics. Subject is electronic devices and circuits. Okay, previous videos I have discussed following topics. Okay, in my description I have provided my previous videos links and notes. Okay, just go through it. You can understand. In this video I will discuss about charge densities in semiconductors and Hall effect. Okay, now just we can recollect all the topics step by step within fraction of seconds, right? See, here insulator, semiconductors, I'm using energy band diagram, discuss the topics. Just in my description I have provided a videos link, just to go through it, right? Okay, mobility and conductivity, okay, these are all topics I have discussed. Electrons and holes in intrinsic semiconductor, right? Extrinsic semiconductor types, n type, p type, then drift and diffusion currents. Okay, these are all topics I have discussed in the previous lectures, right? Now we will discuss about charge densities in extrinsic semiconductor. What? Charge densities in extrinsic semiconductor. Before going to the this discussion, first of all we concentrate on mass action law. So what is mass action law? See here, there is a two types of materials there for extrinsic or impure. Extrinsic semiconductor materials categorized into two types. One is p type material and another one is n type material. Let's start with n type material. If a pure semiconductor is doped with n-type impurities, the number of electrons in the conduction band increases. Okay, number of electrons in the conduction band increases above a level. So underline this point, very important. Let us consider n-type material. Conduction band increases above the level, right? Above the level. Now, the number of holes in the valency band decrease below a level. So is a level is the medium point. So in the conduction band, the conduction band, electrons are above the level, holes is the below level decreases, right? Which would be available in the intrinsic semiconductor. Similarly, in the addition of p-type impurities to a pure semiconductor increases the number of holes in the valence band. Here valence band above level decreases the number of electrons in the conduction band below the level. You can understand this point. Please, once again I will repeat. In n-types impurities, if you add to the pure semiconductor, in the conduction band increases above a level, number of holes in the valence band decreases below a level. Let us take p-type impurities to a pure semiconductor, increase the number of holes in the valence band above a level, decrease the number of electrons in the conduction band below level. Now the because of the rate of recombination increase due to the presence of a large number of free electrons or holes. Now further, the experimental result states that the under equilibrium state for any semiconductor, the product of holes and the product of electrons, like nothing but n dot p constant, and is independent of amount of donor and acceptor impurities. This relationship is known as mass action law, right? Now you can concentrate this important expression. This relationship is nothing but the mass action law. I will underline this point. N dot p equal to ni square, right? This is the mass action law equation, right? Now, based on this expression, we can concentrate on charge densities in n-type semiconductor and p-type semiconductor, right? First of all, let us take, we can think about n-type. So how we can write this n-type? I will derive small expression, you can understand. Now what is our mass action law state? N, right? N dot P is equal to Ni square. This is mass action law. Let us take n-type semiconductor. So now it is converted. Nn dot Pn is equal to Ni square, right? Intrinsic material. Now what about Nn here? Nn is equal to Ni square by Pn, right? This is the final expression. See, remember this one, Nn is equal to Ni square by Pn, right? Now, see this expression, Pn is equal to Ni square by Nn. This is the equation. So, this equation is converted into like this. This equation, Np is equal to Ni square. Now, we can discuss about charge densities in N-type and P-type semiconductors. The law of mass action has given the relationship between free electron concentration and hole concentration. Electron concentration we can find out Nn or some electron concentration. Now hole concentration we can call it as a Pn, right? These concentrations are further related by the law of electrical neutrality as explained below. Now Nd, so here Nd, N type and D means donor, right? N means N type, D means donor. Nd be the concentration of donor atoms in N type semiconductor. See here, N type semiconductor, right? So Nd be the concentration of donor atoms in an N-type semiconductor. In order to maintain electric neutrality of the crystal we have, so this expression can be divided into Nn. So why are called N-type? Nd. So Nd means donor concentration plus Pn. Okay. Now this Nn is tends to the Nd. So here Pn is negligible. Okay, how it will be converts this mass action law? Np is equal to Ni square. Just now I derived one statement. So that is called Pn equal to Ni square by Nn. Now Nn can be replaced with Nd. Here Nd is a donor concentration, right? Where see once again see here Nn and Pn are electron and hole concentration in N-type semiconductor. The value of Pn is obtained from the relation of mass action law. See here, I think you can understand. So here Pn is equal to Ni square by Nn. So Nn can be replaced with Nd. So the final expression Pn equal to Ni square by Nd. So Nd is the donor concentration for N-type. Similarly, you can same expression we can expect from the p-type material. Same we can derive. See here I underline. So Pp is equal to Na plus Np. So because of p-type semiconductor. Why here I write Na? Na means acceptor in acceptor concentration. See here acceptor concentration. Now Pp is equal to Na plus Pp. So you can neglect the Np value. So finally P suffix P equal to Na. So from mass action law we can write Np is equal to Ni square by Pp. These two are charge densities in N-type and P-type semiconductors. Very important question, 2 marks question also. Okay, now we can concentrate on conductivity of extrinsic material in N-type semiconductor and P-type semiconductor. Very simple, you can draw direct equation. Q is equal to Qn mu n, right? Qn is the number of electrons, mu n means mobility. So sigma is equal to Qn mu n. So sigma is nothing but the conductivity. For N-type, sigma n equal to Qnn into mu n. Okay, you can also write mu n is equal to, so what mu n, where we can expect mu? Actually mu can be written as Vd is equal to mu E bar. Okay, this is also one expression, right? So sigma n is equal to Q into n into mu n, right? So based on this expression we can write in N-type semiconductor material, and also we can write for a P-type semiconductor sigma p is equal to Q into Pp mu p. So since Pp is equal to, we can write as a Na. Na means some p-type semiconductor for acceptor concentration, and D means donor concentration. This is the clear explanation about charge densities in n-type and p-type semiconductors. Okay, again I will tell you, the law of mass action has given the relationship between free electrons concentration and hole concentration. Okay, right. For Pn is equal to Na square by Nd, and P is equal to Na square by Pp, right? The next one, a Hall effect. Okay, this is very important. Hall effect for 2 marks and essay answers also. What is the application of Hall effect? By using Hall effect, we can find out the given material whether it is N-type or P-type. Right now, First we will start with the definition. Okay, definition of Hall effect. When a current carrying conductor, see here, this is a current carrying character high. I will underline here. This is the current current conducting carrier or current carrying conductor, right? I is placed in a transverse magnetic field. This all can be treated as a transverse magnetic field. Okay, now the current carrying conductor is placed in transverse magnetic field. Okay, this can be called as a what? Transverse magnetic field, right? This can be called as a transverse magnetic field. The current carrying conductor is placed in this transverse magnetic field, right? Now what is the definition said? When a current carrying conductor is placed in a transverse magnetic field, see, I underline the current carrying conductor is placed in a transverse magnetic field B bar, right? Is B bar. The electric field is induced in the direction of perpendicular to both current magnetic field, right? I will tell you once again. When a current carrying conductor placed in a transverse magnetic field B bar, the electric field is induced in the direction perpendicular to both current and magnetic field. I think you can understand very easy. Hall effect. This is the current carrying conductor is placed in the magnetic field. Now the electric field is induced here. Electric field is induced. How the electric field is induced? In the direction of perpendicular to both what? Electric field and electric magnetic field and current. Okay, this is the definition of Hall effect. Okay, this is the diagrammatical representation. You can also draw in this end examinations. Very important. When a current carrying conductor is placed in a transverse magnetic field B bar, the electric field is induced in the direction of perpendicular to both current and magnetic field. So here there is a two fields are acting. One is electric field and another one is magnetic field. So these two are perpendicular with the current, right? Now we will start with magnetic field or electric, anything, no, nothing to worry. So force equation. So F is equal to BQV. Let us starts with there is a two force equations. At one state, use some centrifugal force. At one state it can be equal, right? The first one, force in magnetic field, simply you can write BQV. So B means some magnetic flux density. Okay, right? Some here, here V, here speed, right? F, F means here force for electric field. Q means charge. E bar means electric field intensity, right? B means magnetic field intensity. E means electric field intensity, right? Now, so what is force for magnetic field? Simply you can write BQV. Now, what about F for electric fields? So F is equal to QE. At one stage, you have to equate these two expressions. First expression BQV and second expression QE. Okay, then here QQ get cancelled. Some BV equal to E bar, right? BV is equal to E bar. Then what about he here? He can be defined as Hall electric field intensity. Okay, so E can be, we can write as a VH by L. So here VH means Hall voltage. Field in terms of voltage, we can write voltage per length. So EH is equal to VH by L. Okay, or V by L. Now what is our first expression? BV is equal to E bar. In this E, you can substitute VH by L. Now we get this expression, that is called BV is equal to V suffix H by L. Now what is our current density? That is nothing but current density, nothing but J. Okay, J we can write J bar is equal to NQV, right? J we can write as J bar is equal to NQV. So what about V? in mobility equation we can also v drift velocity vd is equal to mu e bar, right? Now in this EH is equal to VH by L. So VH by L is substitute to equation 1. So finally we get BV is equal to VH by L. So finally what about drift velocity here? Drift velocity V is equal to VH by LB, right? VH by LB. Now current density J bar equal to NQV. So V is equal to mu E bar for mobility equation. Now J is also called current density, ampere per meter square, and in the sense current per area. So area we can write length into breadth. So W into L. So I by W into L. Now NQV. V you can substitute VH by LB. So this VH by L and this J is equal to I by omega I by WL. Substitute these two expressions, right? See here, very easy. In my description I have provided link, you can understand, right? I by WL and Q, V substitute from here. See here, I can explain. This V is substitute VH by LB in this expression. Okay, now here what happened? LL get be cancelled. Finally, VH, Hall voltage can be defined as BI by W into N into Q. Okay, W into I into this is some magnetic field by into I by W into N into Q, right? What about RH? RH is equal to some Hall coefficient. So RH is also called 1 by NQ. Now replace with NQ value, with RH. Finally we get VH is equal to suffix H. Please remember here, VH is equal to RH, RH also suffix into BI by W. Okay, BI by W. This is the expression for with replacing of RH. Now finally RH is equal to V suffix H into W by BA. RH is nothing but Hall coefficient. Now J bar is equal to NQV. This is the expression for J bar is equal to sigma E bar for conductivity. Just you have to concentrate only two equation. One is Hall voltage and second one is the Hall coefficient, are also called RH. VH is equal to BI by WN into Q. RH is equal to VHW by BI. Okay, these two expressions are very important for doing the mathematical problems. Okay, J bar is equal to sigma E bar for conductivity equation. Mu N suffix or mu is equal to sigma RH also we can write. This is for the mobility expression. If you want any relationship between mobility, you can also write this one also. Mu is equal to sigma RH. RH means Hall coefficient, right? The next discussion I will discuss remaining topics. In this my description I have provided all concept links. Just go through it. At the same time I have provided notes links also. Just go through it. Thank you so much.